This is the first of about 3 to 4 videos on a topic that's really important in chemistry, stoichiometry. Stoichiometry is basically a method for solving problems using a balanced chemical equation. And those types of problems include questions like, how much product should I get in this reaction? What is the percent yield after I do get some product and I weigh it? How much should I have gotten and how much did I really get? So that's like a percent yield of what you could have theoretically achieved in the reaction. So because chemistry, of course, is about reactions, and we need a way to kind of quantify how well did it go, well, there you go. That's stoichiometry. Stoichiometry is using the chemical equation to solve problems. The chemical equation is the balanced reaction. We can refer to it as a chemical equation showing how to get from reagents to products, or we can call it a balanced reaction. So the first thing we have to do is always know how to write the equation. What are the reagents? What are the products? And then we have to balance. So writing and balancing equations is part of the task for, I guess, stoichiometry. It's before, in a sense, before you do the stoichiometry. You have to write and balance a chemical equation. You need to know how to do conversions through those equations. So this work that we use, or this work that we do through stoichiometry, requires you kind of dust off those ideas you had in the past, maybe with the first test in chemistry, on conversions, where we take some number, let's say a gram amount of something, and we convert it to moles. We'll use those types of conversions, I guess, in the process of stoichiometry. So it becomes important that you remember how to cancel your units, how to see the calculation moving from one measurement to another. That's the first 2 videos that we'll have. The third and fourth videos will cover types of reactions. So we need to know certain types of reactions, just be familiar with the major categories. So formation, or we'll say precipitation reactions. Precipitation of salts in water becomes very important. For example, silver and chloride can get together to form a precipitate, AgCl, silver chloride. And we can introduce those using 2 different salts, maybe silver nitrate and sodium chloride, to get our desired precipitate. Acid-base reactions. So it's all about the proton. We're going to be talking about transfer. Someone grabs the proton, H+, and takes it, and someone donates it. So we're going to be talking about that's our currency, you might say, what's being transferred in the reaction. Then last but not least, oxidation reduction reactions. It's all about the transfer of not protons in this case, but electrons. Electrons is what the currency is in those types of reactions. So in general, again, we need to write and balance chemical equations. So here's one that's, I guess, a favorite in summer times. You take your coal, your briquettes, and you burn them. You add a little bit of heat, so we can maybe say add a little bit of a flame. But once it starts going on its own, and it starts producing a whole lot of heat that I can use to grill my burgers. What we've done there is we've taken carbon from this charcoal briquette, we've added oxygen, and we've made CO2. And in that process, we've also generated some heat. So you'll sometimes see heat as an actual product of the reaction. That's what we use our charcoal briquettes for, is to make that heat. Here's my burger. or a hot dog you can cook. So that's kind of why we want to follow reactions. We'd like to know which ones produce heat, which ones don't, and we can use those in our everyday life. Some symbols you'll need to know as you look at reactions. The arrow is the big one. Arrow tells you, hey, I've got a movement of something here on the left side, reagent, over to something on the right side, product. It's an action arrow. It's like a verb. The reagents reacted to form product. Reacted is a verb. It changed to form product. It was burnt to make product. The arrow is everything. It's the predicate. It's the verb. And the object and the subject are kind of like your reagent and your product. just some plus sign just means we're going to have 2, maybe 3 reagents. We'll have a plus sign between them. S, L, and G are the phases. Aqueous, when it comes to precipitation reactions, we introduce our ions that might come together. We introduce them through solvate already dissolved in water. And then this little symbol here, this little delta, is for heat. You also might have light, H nu, as a part of your symbol on top of an arrow saying the reaction was irradiated. So again, our goal for this first video is just going to be writing and balancing equations. So in most cases, the instructor or professor will have you start with some unbalanced equation. So let's put this unbalanced. But they've already kind of given you what are the reagents and what is the product. They haven't just given that in text. They've given it in their molecular formula. So if we look at this one, we can just kind of see the problem. And that's what I want to do with this slide, is just that you see the problem. I've got 2 hydrogens on this side, and I have that over here. The 2 here is a subscript, meaning that there's 2 H's for every 1 oxygen in this thing called water. And of course, this is just the elemental form of hydrogen and the elemental forms of oxygen. But these come together. One of these plus one of these can make at least one of these, but we have a problem. I have 2 oxygens here, but I only have 1 oxygen here. So that's not balanced. It's an unbalanced reaction. We're going to learn how to balance these. Oh, and we can't change the compound. You don't use these numbers to change anything. They come set. They're part of the molecule. But we can change what's called the coefficients, the numbers out in front of the molecules. So just before we get into kind of how to balance, remember what the chemical equation is illustrating. So for example, for a hot dog equation, we'd say 1 bun plus 1 dog gives 1 hot dog. So we can say whether it doesn't matter that there's 4, 4, and 4, the simplest ratio is 1, 1, and 1. We always go down to the simplest ratio when we're trying to balance an equation. So no matter how many hot dogs you need to make, you'll have a 1-to-1 ratio of the reagents, we'll say. Here's our action arrow. 1 dog plus 1 bun makes 1 hot dog. And we can also talk about these in terms of moles. We don't have to say 1 to 1 in terms of number of actual molecules. We can say this is representing 1 mole, 6.02 times 10 to the 23rd. It's like a chemist's dozen. We could say 1 mole of this plus 1 mole of this. There's 2 moles of hydrogen gas plus 1 mole of oxygen gas can make 2 moles of water. We don't have to use just the smallest number, 1 hydrogen molecule plus another hydrogen molecule is 2. No, we can say like a dozen. We could say 2 dozens of the hydrogen molecules, 1 dozen of the oxygen molecules makes 2 dozen of the water molecules. And a chemist uses a much bigger dozen kind of unit. We use the unit moles. So we can speak about reactions in 2 ways. As between atoms, and that's true. We could talk that way. But we can also speak of it as between moles of these same reagents in that same reaction. In that same proportion, I guess. Ratio. Has to have the same ratio. Now, I've just kept it up here in the molecular form. We are doing a counting many times to make sure the numbers of atoms or numbers of moles are equivalent. 4 H's on the left side of the reagent side, 4 H atoms on the right side. But we again could say 4 moles to 4 moles, 2 moles of oxygen to 2 moles of oxygen. Nothing is gained, nothing is lost. Conservation of mass. So here's how we can start. This is going to be the slow method first I'll talk about. It's called the kind of the ledger approach. Make sure all reagents and products are shown correctly. For example, you can't have like H4O. That's not a true compound. You have to have real compounds, H2O, CO2, sodium sulfate, things that are real. You have to make sure you're writing the formula correctly. And then we can count as part of our step 2. We can count the numbers of atoms of each element on each side of the equation. So the reagents, count everything on the reagent side and the product side. And then we can use coefficients to balance things. We can't use any other numbers, just the coefficients that are out in front of these molecules that might be in a balanced equation. Now the fast approach I'm going to use for the second practice problem we do, and that is a really big idea. We call it the big compound method. We'll call it the BCM, big compound method. Find the biggest compound, set his number of how many there are of him to 1, and then use that to set everybody else. And we can use fractions if we need to, but we'll always have to double the fraction to get rid of it. And you'll see more about that as we go here. Let's talk about the slow method for our first one. So here's an equation that's unbalanced, so it's not balanced. So we're going to go ahead and balance it. Well, the first thing, because we've already started with, is that these are real compounds. They're not drawn incorrectly in this imbalanced equation. But the step 2 was count atoms on each side. So the number of oxygens on this side would be 2. Numbers of oxygens on this side would be 3. So right there you might want to put a star and say, oh, I got to come back to that possibly. Number of carbons on this side is 1. Number of carbons on this side is 1, so that's looking good. And the number of H's, looks like we have another problem. It's 4 on this side, and we have 2 on this side. So there you go. That's your step 2. First part is just to see where is the problem. It's on the oxygens and the hydrogens. So we said already, we counted those atoms on each side. This is just what we just had. We need to balance the equation. We need to make sure we can now change the coefficients out in front to set it right. And we're going to start with hydrogen in this case because the oxygen by itself, you always do that one last. When something's by itself, do it last because it kind of can be used to clean up whatever imbalance you have, because once you change his coefficient, it doesn't change the H's or the C's. So if I went ahead and worked on the H's, remember we had those off. This was only 2 on this side and there's 4 over here. I'm going to put a 2 out in front of there. That gets me to the right number of H's, so they're checked. And that changes the oxygens because 2 out here changes this from 1 oxygen to 2 oxygens. And those 2 plus these 2 is equal to 4. And on this side I only have 2. So you can kind of guess what I'm probably going to put right here as a number to balance this oxygen. We can say let's put a 2 out front there. I apologize, I forgot to put the unit telling us what kind of phase we have. So we multiply that on the left by 2. That's what we used. And we did the initial work on the hydrogen. We put a 2 out in front of the H2O to get the H's correct. That caused a difference here, but we balanced that difference from 4 to 2 by putting a 2 in front there. This is the slow method. I want to just talk to a bit about the fast method, and we will be done. So if we have an equation that's imbalanced, certainly there needs to be more iron, Fe, because there's 2 over here. This is kind of the BCM method again, the big compound method. I notice this guy's really big. So what I can do is I'll just set him to 1, just as a starting point. Instead of like arbitrarily just starting to count atoms for an unbalanced reaction, you can kind of say, well, if I set him to 1, I can cause all the other ones to be set. Well, I'd have a 2 out here. So let me make sure. So I'll put a 2 out here because there's 2 Fe's in one of these iron oxides. And for this one, 1 times 3, of course, is 3. I need a number times 2 that's equal to 3. Well, what I can do for now is I'll just use 3 halves, or you can say 1.5. But what I can do is just double everything, because this is now balanced in terms of actual, we don't want to use fractions, but 3 halves times 2 is equal to 3. We need to get rid of that fraction, though, or this in fraction form. So what do? We double everything. So 2 times 2 is 4, plus 3 halves times 2 is 3, And 1, there's an implied 1 out there. We don't have to show it. 1 times 2 is 2. So we can now say that's our balanced equation. This is called, again, the BCM method. We'll call it the biggest compound method. If you have one that's really big, set him to 1, set everybody else, and then if you have to double to get rid of a fraction, do it. Hey, thanks. That's it. Bye-bye.